So you've made it. We're at the last section for this course, and this can be a doozy. So we're going to go through this very slow and methodically. We're going to go through the content in a little bit of an old-fashioned way just to make it a bit simpler. And certainly I encourage you to contact me with any questions that you have. So this section is about the central limit theorem and also about confidence intervals. So we're going to begin with this idea of something called a central limit theorem. So let me switch. And you can see that I'm going old school paper and pencil here to walk you through this. So the central limit theorem gets to the question of what happens to X bar if the population is not normal. Well, we know that as the sample size increases, that the distribution is going to get closer to normal. And in fact, if a simple random sample of size n is drawn from any population, when n is large, the sampling distribution of the sample mean X bar is close to normal. And it has a mean of mu and a standard deviation of sigma over the square root of n. So how this is used is, up until this point, we've said if one person is selected, if a male, if a woman. Now we're going to start looking at what if 42 women? What if 33 men? So that number is going to change. So rather than just sigma, sigma will be given by dividing by the square root of n. So what I want to do is actually look at one of your homework problems. So I'm going to share the screen. And you should be looking at homework problem number 1, which gets to this very idea. So assume that women's heights are normally distributed, mean given by mu equals 62.6, standard deviation of 1.7. Part A is what we've always done. One woman is randomly selected. Find the probability that her height is less than 63. Then we change it. We say, what if 42 women are selected? So I'm going to stop sharing that screen, and I'd like for you to look at what I've done here. Here's the two problems. A little bit of summary of information that you were given. We knew that mu was 62.6, sigma is 1.7. So let's look at part A. Part A is here on the left. No different than what you did in the previous sections. Take X, subtract the mean, divide by sigma. Okay, that's going to give you your Z value, and then you can use your chart. Now, when we have 42 women, what we're going to do is divide by the square root of 42. And you can see that Z significantly changes. You're also going to notice for these particular questions that suddenly there's not a chart given. So I want to show you how you can find this probability on your graphing calculator. Okay. So if you go to second vars, you'll see there, number 2, normal CDF. And what that's finding is the cumulative, that's what the C is standing for, the cumulative area underneath of a certain value. So we're going to go ahead and select that. And then you have to provide some information. You need to provide the lower boundary. So if it's a less than, that lower boundary's got to be really far to the left. So a good number to put in is just negative 1,000. The upper boundary is going to be your X value. So in this case, it's 63, comma 63. And then you're going to put in your mean, 62.6. And in part A, it's just 1.7. So there is your probability, 0.5930. You could have also gotten this by looking it up in the table, but I do want you to practice with your calculator for this because not all problems in your homework will be giving you a table, so I want you to be able to do it both ways. We could also do part B on the graphing calculator. Again, it's just a normal CDF. It's still a less than, so my lower boundary I can make negative 1,000. My upper boundary is still 63. My mean is still 62.6, but now my standard deviation rather than 1.7 is 1.7 divided by the square root of 42. And I can literally, oops, let's fix that. I can literally type that in without having to figure it out. And I'm going to get 0.9364, and that is in fact the probability for part B. Okay, so let's look at another homework problem. The first few are pretty much always completed the same, but let's try another one. Excuse me. The capacity of an elevator is 12 people or 2,052 pounds. The capacity will be exceeded if 12 people have weights with a mean greater than 171 pounds. Suppose the people have weights that are normally distributed with a mean of 174 and a standard deviation of 28. Find the probability that if a person is randomly selected, his weight will be greater than 171 pounds. So let's go ahead and do this. So again, you really have two options. Your first is to go ahead and find Z, which I have found is negative 0.11, and I'm looking for the probability that Z is greater than negative 0.11, so I'd have to look that up correctly. Or I can use the graphing calculator. So you can see here that I've already gone to normal CDF. My lower boundary this time, though, is 171 because it's greater than. So I'm starting at 171. I'm going to go up to positive 1,000 because it's a greater than. My mean is 174, and my standard deviation is 28. When I enter that, I get 0.5427. Okay, now part B looks a little bit different. So let's share the screen again. Part B says find the probability that 12 randomly selected people will have a mean that is greater than 171. So the only difference here is that rather than sigma, we're going to use sigma over the square root of n. So I'm going to stop sharing. I'm going to pop back over to the graphing calculator, and we're going to go ahead and enter that in. So you can see here that I've already gone ahead and entered it. Notice the only difference between the two parts with the central limit theorem is rather than standard deviation being 28, I'm going to make it 28 divided by the square root of 12. So we'll spend a lot of time in this section really examining this idea of the central limit theorem. And we'll look at it a variety of ways. So in this problem here, the amount of time employees at a large corporation work each day are normally distributed. Mean is 7.7, standard deviation 0.33. So what we're getting at here is if the sample size is 23, the mean doesn't change. The mean is not affected by the central limit theorem. What is the standard deviation. So I took my standard deviation of 0.33 and divided it by the square root of n. So in this case, if I go to n being 38, what do you think is going to happen to the mean? Nothing. We should still be able to enter 7.7. What's going to change is the standard deviation. So in this case, we'll take 0.33 and divide it by the square root of 38. I really want you to spend a good chunk of your time practicing that idea. If I just have one item compared to 30 items or 12 items, the number that's going to be affected by with that central limit theorem is going to be the standard deviation. That brings us to the topic of confidence intervals. So confidence intervals are what we consider statistical inference. An inference is pretty much an educated guess. Statistical inference provides a way to draw conclusions about a population from a sample. So it lets us make some educated guesses about what would happen in the full population from what happens in a small subset of that population. So when we talk about confidence, if I'm 95% confident, then in 95% of all samples, the unknown that goes with the population will be able to be said to fall between two values, which we'll solve for. So, confidence intervals are found by taking the estimate, which if I'm using an estimate for mu, that's going to be x bar, plus or minus the margin of error. And I get the margin of error by doing the calculation that you see here. Now, what in the world is that z star referring to? Well, that depends on the level of confidence that I'm looking for. So if I'm 90% confident, I'll use 1.645. 95% confident, 1.960. 99% confident, 2.576. So the margin of error is that piece of it. Now, some of you will try and do this by hand. That's fantastic. Okay, you do x plus that calculation, x bar minus that calculation, and you'll have your confidence interval. We can also find a required sample size using this piece of the equation. So let's suppose that we have an IQ test, and I want to know, let me go ahead and pause and share my screen. I want to know the sample size necessary to estimate the mean IQ so that it can be said with 95% confidence that the sample mean is within 4. Okay, so let's write down what we know, and then I'll go ahead and share my screen again. I know that the mean is 100. Standard deviation is going to be 22. And I know that my margin of error is going to be 4. And we want to determine with 95% confidence what n needs to be. Okay, so let me stop sharing. Let me go back and let's show what we have. So remember that we said that the margin of error is equal to z star times sigma over the square root of n. In this case, I know the margin of error is 4. 95% confident, which makes z star 1.96. Standard deviation is given, and we can solve for n. So the first thing that we'll do is divide both sides by 1.96. I'll do this in a couple of steps. You may not require this many steps. So we have 4 divided by 1.96. Okay. Now I can go ahead and invert both sides. multiply both sides by 22. And then I can square both sides, and that should give me my n. Let's go ahead and do that. When we go ahead and do those calculations, we end up with 116.2. Now, when we go to enter that, it's going to direct you to round up to the nearest integer. So we would actually need a sample size of 117 to ensure that that 4 will happen. 116 would not be enough. So in those cases, we're always rounding up. Let's look at another example. Another question where we're trying to find the minimum sample size, and we're using the idea of confidence intervals and the margin of error to do that. So we know that we want to be 90% confident that the sample mean is within 13. So in this case, the margin of error is 13. Since we want to be 90% confident, that 90% confident is going to go with what value? Let's go ahead and look that up. Okay, so the Z star that goes with 90% is going to be 1.645. We know that sigma in this case, okay, so it's within 10. Assume the standard deviation of the population of monthly time spent on the internet is 218. And then we're going to go ahead and solve for n. We're going to solve for it just like we did over here. Okay, so the first thing that we can do is divide both sides by the 1.645. So then we have 218 over the square root of n. I'm going to go ahead and flip each of those. Multiply both sides by 218. And then I'm going to square both sides to get n. Okay, so you're going to spend a few problems just practicing with that idea of margin of error and using that to find n. Then you'll spend just a few problems actually getting a confidence interval. So we could do this by hand. Okay, I know that it's going to be x bar plus or minus z star times sigma over the square root of n. And I could do that by hand and get the lower limit and the upper limit. But I encourage you, just to save some time, to use your graphing calculator. So I'm going to go ahead and record that information that you see on the screen there. So we know that x bar is 45, sigma is 9, n is 47. I'm going to stop sharing. And I want to show you how you can go ahead and do this using the technology. Let's let that focus just a minute. There we go. Okay, so to find your interval, we're going to go to Stat, arrow over to Tests, and you'll see one here called Z interval. Now, sometimes it'll be very specific and say, use T. Then you have a T interval. So we're going to click on Z interval for this first one. And we're going to either put it in by entering data, or we're going to enter it, which would go into our lists. But in this case, we don't have data. We actually have some summary statistics. So we're going to enter it. Sigma is 9. X bar is 45, N is 47. Confidence level is 99%, and we're going to say calculate, and there it is. It's beautiful. It's that simple on the calculator. We're going to do one more, and then I think you're ready to get started practicing with central limit theorem and confidence intervals. In a random sample of 45 refrigerators, we have the mean repair cost, $110. Okay, so we know N is 45, We know that the mean is 110 and the standard deviation is 1590. We want a 90% confidence interval for the population mean repair cost. And then we're going to interpret that. So I'm going to stop sharing. Let's go ahead and enter that in. We're going to go to Stat, Tests, number 7. In this case, standard deviation is 15.9, X bar is 110, N is 45, and our confidence this time is 90. We'll calculate it, and then I'm going to go ahead and enter that so we can do the follow-up question. So it asks you to interpret it. So let me go ahead and flip back so that you can see how this question is worded. How would you interpret this? With 90% confidence, it can be said that the confidence interval contains the true mean. The confidence interval contains 90% of the mean repair costs. Or with 90% confidence, it can be said that the confidence interval contains the sample mean. Well, we always use the confidence interval in hopes of capturing the true mean. So you can see that when we select that, it is in fact correct. So I want you now to do some practice. Use that idea of central limit theorem. It's directly related to the margin of error. That margin of error ties directly into confidence intervals. And let's see how you do with using the technology to make those processes a little bit easier.